Higher Notes 1.1 Motion Equations and Graphs. This is part 4, where we're going to look at the velocity time graphs of a ball undergoing 3 different motions. A, it will be falling downwards, just dropped and then landing. B, thrown up in the air, so that it will go up, reach its highest point and come back down again. And bouncing, so that it's dropped from a height, reaches the ground, bounces, comes back up, reaches maximum height, comes back down, and so on and so forth. So the velocity time graphs for these are quite interesting, so we're going to look at them carefully. So a reminder of the sign convention. Very important in this context. We will be using this throughout. The sign convention is for vectors which can change direction, and so we need to know whether they're going up or down, left or right. So the convention, of course, then is that up is positive. So if a vector, the 3 vectors we deal with, remember, are displacement, velocity, and acceleration in this context. The same would apply to force, but we're not really looking at forces in this section. But if the vector is pointing upwards, so the displacement is up, the velocity is up, the acceleration is up, then that's a positive quantity. But if it's down, then it is negative. And the most familiar example of a negative vector pointing down is the acceleration due to gravity, which is always minus 9.8 in any contexts where direction is important. Similarly, if you're going to the right, that is a positive vector, whereas if you're going to the left, then that is negative. That right-left vector sign convention becomes quite important in momentum and collisions, where the body could be going right, could be going left, as you'll see when you study that section. Okay, so throughout this then, remember the vector sign convention, mainly the up-down aspect of it in this case. So let's now look at part A, the ball falling downwards. So I'll give you the situation diagram. It's very simple. We have a ball and it is simply dropped and it free falls downwards and reaches the ground under gravity. So what would its velocity time graph look like? Well, when you're drawing velocity time graphs, remember it's velocity, not speed. So sign matters, direction matters, velocity is a vector quantity. So when we're drawing these graphs, you always need to have your y-axis, but you need to have your x-axis such that you've got a positive and a negative y-axis, like that. Okay. So, always put in your origin, its velocity. Let's always assume this is a velocity time graph unless you're explicitly told that it's speed. Okay. Well, in this particular case, the ball is dropped from rest. Perhaps we should put that in. It's at rest initially. And if it's at rest initially, then obviously the initial velocity is 0. So our graph begins here. When time is 0, velocity is 0. Perhaps we could just add in here that this is the positive part of the y-axis and this is the negative part. And what that means is that if the value of the line, the points plotted, is a positive velocity, that means it's going up. And if it's negative, it means it's going down. Now, a ball dropped from rest and just falling under gravity, under free fall, begins accelerating under gravity at 9.8 meters per second and continues until it hits the ground. It's going down at all points, at all times, and so its graph is a uniform acceleration downwards, and the line would look like that. Negative gradient means negative acceleration, but the actual sign of the velocity at all points in time is negative. So at all points in time, that ball is falling downwards. Okay, and at time t, this is where it would hit the ground. And at that point, it's dropped. And this is an acceleration downwards at g, which is minus 9.8 meters seconds to the minus 2. Okay, so that's the graph, the velocity time graph of a ball falling downwards. Part B was the ball thrown up in the air. So the situation diagram for this is this. I know that in real life, a person throwing a ball is already standing in the balls maybe a meter or so above the ground, but we'll just take it as if it's going from the ground itself. So the ball goes up, reaches the highest point, and then comes back down again, like so. Now I've made the ball look as if it's displaced slightly to the right. If it was an absolutely vertical throw upwards, it would be straight up and straight back down again. But this is just for clarity, okay? So clearly it is launched at a particular velocity u. It comes back down at a particular final velocity v, and if we neglect air resistance, then by symmetry that will be the negative of what u was. Same value, just opposite sign. At this point, of course, velocity is 0. Obviously this is the up section and this is the down section. And on the way up, the body is decelerating at g, so it undergoes a negative acceleration, an acceleration of minus 9.8. And on the way down, it is accelerating at g, because the acceleration vector is in the same direction as its velocity vector there, so it's accelerating. So of course that's a deceleration up, but this is an acceleration down. Okay, now all of that analysis will be revealed in the velocity time graph. So again, we need both positive and negative y-axes, time in seconds, velocity in meters per second, and there's the 0. Well, the thing to note about this motion is that right at the start, the body is launched upwards vertically. So when the clock starts at t equals 0, it already has a velocity, which I'm calling u here in fact, and that's a positive velocity because it's going up. So the very start of the line is here, where we've got some initial velocity u. If you look at our situation diagram, it then moves upwards, and as it does so, it decelerates, it slows down until it reaches the highest point. So its velocity at all times on the way up is positive, so it's always above the x-axis, but it's getting smaller in magnitude. So it's a uniform deceleration, in other words. So we're going to get something like this happening. And you can see that at that point the velocity has become 0. That's it reached its highest point. After it's reached the highest point, it begins, instantaneously its velocity is 0. It then begins to accelerate back downwards under gravity. Now the acceleration downwards is minus 9.8 meters per second to the minus 2, and the deceleration upwards was also minus 9.8. So the gradient of this velocity time graph line must be constant. It's always minus 9.8, so it's always a negative gradient, so the line is always sloping down to the right. And what it does then is, on the way back down, it carries on like so. And there we have it. Let's just pop in our construction line. So this value here, that would be the time of flight for the whole motion. Okay. This point here is the top of flight. And that, by symmetry, that's half the time of flight. So that would be a half t there on the time axis. Okay. Notice finally then, gradient of a VT graph equals the acceleration, which at all times is g, which is minus 9.8 meters seconds to the minus 2. Constant gradient, always negative, always sloping down to the right. One final observation here. Notice at half t, that's the halfway point, the top of the flight, the ball is still accelerating there. The VT graph still has a gradient of minus 9.8, and it can be tricky to understand that, but the ball is still accelerating even though it's at the top of the flight and is momentarily at rest. And the reason it can be accelerating while it's temporarily at rest is it's changing direction. Velocity is a vector quantity, so if the direction is changing, the velocity is changing, therefore it's still accelerating. Okay, so that's the velocity time graph for a ball thrown up in the air. Our final scenario is the bouncing ball. And each of these has, in graphical form, come up in past papers at various points. I'm going to take the whole width of the page here to draw the situation diagram. So here's the ground. Now, in this situation, we're going to take the ball and let it drop, and it's going to come down vertically, just drop vertically downwards, bounce and go back up again, and then come back down and bounce. So it'll bounce several times, and gradually the height of the bounce decreases as energy is lost, and it ends up stationary on the ground. Now, strictly speaking, it just goes straight down and then straight back up again, but I'm going to do what I did here, and I'm going to displace the ball slightly to the right just to let you sort of see what's actually happening. So we're going to imagine then the ball comes down and it bounces, and it's then going to go back up again, but it won't go as high in the second bounce because it's lost energy during the bounce itself. And then that continues and could go on for several bounces. Every bounce causes the ball to lose energy as sound and heat. There's also a bit of energy lost as it moves through the air. So the maximum height reached each time is always less. Okay. So this is bounce number 1, and this is bounce number 2. I'm only going to deal with the first couple in the graph. You could go on, of course. Okay. At the top of the flight, remember, V will be 0. V is also 0 at the very beginning because it's dropped from rest. Okay. So that's the situation diagram. Put some arrowheads on just to show direction. Remember, in real life this would be straight up and straight down, but we're causing a sideways displacement for clarity. Okay. Now, one thing to be aware of is that during the bounce, the ball is going to become compressed. I'm exaggerating this to some extent here. Okay. So one observation to note: the ball compresses as it lands, and decompresses as it leaves the ground. Now, compress just means it gets squashed, and decompresses, because the ball has got a kind of springiness, the decompression is when the squashing has reached its maximum and then it opens up again back to its normal round sort of size. Okay, right, so think carefully about that scenario. while I now draw the velocity time graph, and you should be thinking about this. These questions are generally found to be very difficult when they come up in past papers, so you will need to think carefully and possibly revisit this graph a couple of times to fully understand what's going on. Okay, so remember, this is the velocity time graph I'm drawing. Always have our origin, time in seconds, velocity in meters per second. That's the positive axis, and that's the negative. Well, remember, the ball is dropped, so it begins at 0 meters per second. And it falls downwards under gravity, so we've got a particular downwards acceleration, so a negative gradient. Okay, like so. So this is what it's going to do. Falling downwards under gravity. And at this point, let's make it go slightly further. At this point, it's going to hit the ground. So it first comes into contact with the ground now. And as soon as it hits the ground, it undergoes a pretty rapid deceleration. This is the compression aspect of the bounce. So it's just touched the ground now, and it's now going to slow down very rapidly to rest. Now it's still moving downwards, but it's decelerating rapidly. So a deceleration downwards means the velocity is always negative, but its value drops very rapidly to 0. Okay, so that is its full downwards motion. It's falling downwards under gravity, and then it's hitting of the ground, and it's rapid deceleration to rest. Notice the steepness of the deceleration to rest whilst in contact with the ground is a much steeper gradient than the falling under gravity, because it's a much more rapid deceleration than it was acceleration downwards. Okay, let's just get some indication of construction line there. So I'm just taking a wee note of the kind of final velocity reached. So by this point we are halfway through the first bounce, and you've got basically the compression section there, that steep line going up to the right. The ball's come to rest. Of course, once it's come to rest, it then starts decompressing, and it's going to accelerate up the way, still in contact with the ground, at the same acceleration that it was decelerating at. Now just watch how you draw this line, because you don't want it to go as far up the axis as it came down, because it loses energy. So when it emerges up from the bounce, it's not coming up as fast as it came down. It's now reached the end of the bounce, it's moving upward, and it's lost contact with the ground, and it's now going to move up but decelerate upward. So I want to get this graph to be the same gradient as my initial section, and it does this. So this is it moving upwards, slowing down as it does move upwards, and it's now reached its new maximum height. Now once it's reached its new maximum height, we're effectively back to where we started, and the motion just repeats itself, but each time the ball doesn't go as high, and therefore it doesn't go as fast. So this continues. I'm going to kind of exaggerate the bounce there a bit. And that pattern repeats again and again. Okay. So that's the story. I'm just going to go back up here and name some points. So if we call this point A, where it's dropped, call this B when it comes into contact with the ground, and C when it leaves, D when it reaches the highest height, E when it comes into contact with the ground and the second bounce, and F when it leaves, and then that will be G, and we'll stop there. I'm now going to put all of these letters on to the graph so that you can compare the two. So there's A, that's where I leave, that's where the ball is dropped from, and then B is when it first contacts the ground. So first contact with ground. Okay. This is an acceleration down between A and B. This section is the compression. I'm going to write that sideways. And the compression takes place between B and C. No, I beg your pardon. We said C was when it leaves the ground, so that's actually C up there. So that BC section involves the compression and then the decompression. And here it leaves the ground. So the B to C section is basically the whole of the first bounce. Okay, we've then got an acceleration downwards. Of course, that equals G. I beg pardon, that's nonsense. This is the deceleration upwards bit, because it's just left the ground. Deceleration upwards. You can tell it's upwards because the velocity is positive at all times, but it's a decreasing velocity. Okay, so it decelerates upwards, and then it reaches the highest point again. So this is the highest point number 2. This, of course, is the highest point number 1. No. Forget that last bit. What we've got there is correct. Okay. If you did want the original highest point, you would say ball released in there. Okay, so it's decelerating upwards now. It's reached its highest point, and it then accelerates down. Again, and here you have the second contact with the ground, and the cycle repeats itself. So you'll probably need to study this one carefully, and probably more than once, but hopefully you have understood the details of how the velocity using the sign convention varies for a bouncing ball. As I say, this is about as complicated as you're ever likely to get. And that brings this note